Okay.
You started the stream. Let's see how it goes. So I think there will be some lag until
Yes.
we see it on YouTube. I think it works.
It works?
Looks good. Yeah.
Okay. Okay. Then let's start, Fabian. Hello and welcome to this stream of Real Analysis. Our idea here today is that we solve some problems. So we calculate, you see already some exercises here, and then we hope that it helps, that we show how the solution looks like. But I will not do that alone today because you see, I'm joined by Fabian. So hello, Fabian. You also have a YouTube channel. So maybe you can tell about that first.
Yes, so thanks for having me today. I'm looking forward to this session of solving some exercises with you. I'm Fabian. I also have a small YouTube channel where I do three things. One is I talk about my research. You will find some talks I gave in seminars there. I have also a series of past recordings on image processing exercises that you can follow along. And I also recently started out to experiment with other formats. One is doing some review videos from the bright side of mathematics.
Yeah, so that's definitely
functional
nice.
Analysis. Yeah. So we'll see where it goes.
Image processing, maybe I can ask there. This is mathematics because it sounds like Photoshop.
Yeah, that's a good question here. I would say it's about some of the mathematics behind Photoshop.
Yeah.
So
okay.
To really capture it in one sentence. Yeah. So we will do some basic operations, and these basic operations you will find in Photoshop, in GIMP, and in other image processing software.
Okay. And what is the audience there? Who wants to learn about that? The mathematics behind Photoshop.
Oh yeah, it's a broad audience. It's from computer scientists, engineers that also do image processing in their experimental setup, and up to mathematical researchers who are more interested in the mathematics that power these methods. Yeah, that are far more general than just image processing. So image processing, or the mathematics behind it, uses a lot of methods from mathematics that you find also in other places, like partial differential equations and variational calculus. These are broad principles that, well, have also an application in image processing.
So you apply a lot of facts from there.
Yes. Yeah.
Or in other words, it's not an easy topic. You have to know a lot about partial differential equations and maybe some function analysis. So not easy.
We start out with some really easy concepts with like histograms and interpolation, and we end up with topics from variational calculus, functional analysis, and also some distribution theory. So
distributions. I also have videos about distributions, so maybe you need to watch them before your image processing. But okay, the audience can decide what they need. So
there's also some participation from the chat. Hello everyone.
Yes,
it's nice to see you're participating and telling us from where you are watching. This is really nice to see.
Yeah, please do that. I also answer questions from the chat. There's the question if this session will be available afterwards, and I say yes. If nothing completely strange happens, we will just upload that as a normal video afterwards. No, there's no Telegram or Discord server. But yeah, we don't need that right now. Maybe
I
in the
would
future.
recommend if something seems unclear or you want some immediate reaction from us, then post it in the chat.
Yes. So, just use the chat.
We can see it and then hopefully react to it, because the idea is that this is a much more interactive session than just watching a video.
It should be. That depends. Yeah, of course. We are live, so also we make mistakes maybe. So therefore, the chat can be helpful. So this is
Yeah,
different
indeed.
than a recorded video. Therefore, we wanted to do that live, that you see also the process in solving an exercise. So which includes some mistakes or some thinking process. And that's also the reason we do that with two people today, because then we can check each other. I hope that this works. And
Yeah,
also,
we'll see.
yeah, okay, we do real analysis. So you see, we've put some exercises in the link in the description. Two of them are already here on the screen. And the topic, as the title says, is series. So series from real analysis. And in particular, we will talk about convergence or divergence of series. So Fabian, maybe you scroll up a little bit, because the question is hidden. It is about, yeah, is the first, maybe we start with A, is this first series a convergent one or a divergent one? And I would say, Fabian, we can immediately start with that. So it's a good starting point. We just start with a concrete, explicit series and calculate. So
yeah, perfect. Sounds good. So yeah, this is a very classical topic that I think is covered in most of real analysis courses. And also the series, the first series I have here today is also a classical example that is non-trivial to solve. And yeah, we'll dive into this. So the first thing I would say, if one is given a sequence like that, the first thing, or a series like that, would be to take a look at the members that we are summing. So usually we denote them by an, when n is our summation index. And we see here that it's the factorial of n over the nth power of n. So this seems very a little bit weird, maybe, but we can analyze a lot here and yeah, find out about which of the two terms in our fraction is really determining whether the series will converge or not. So I would always start, if you find something that looks as complicated as that one, to write down the first elements of the series that we summing up. So A1, so plugging in the value n equals 1, this would mean we have the factorial of 1 over 1 to the 1. So this is really easy to calculate. I would say this equals 1.
Yes, this was not so hard.
So this was not so hard. So let's do the second one as well. And the idea will be that we see some sort of pattern, or that we generate some feeling about how these members that we are summing up behave for larger values of n. So we can come up with a strategy to prove convergence or divergence, because up to now I would say we don't know yet what is happening here, and the first member won't tell us anything about it. So let's take a look at the second one.
In some sense, finally, many members will not tell us anything, but yeah, you want to get the idea of the limit.
Yes, I want to see if there's some trend that we can follow on to really make a rigorous proof. So this also can be calculated easily. So the factorial of 2 is 2, and 2 to the 2 is 4. So also nothing interesting happening here. But once we start looking at the third, it gets more interesting, I would say. So here we have the factorial of 3 over 3 to the 3. And what we can see here is that once we resolve the factorial, so we have here 3 times 2 times 1. So we have 3 factors.
The same as in the denominator, I would say.
Yeah, correct. And here we have 3 times 3 times 3. So, and now, as you may recall from other exercises that you did in real analysis, it's sometimes a lot about estimating something against other numbers. So it really helps to identify some sort of structure here in these fractions. And one that I would say, can be observed easily once we factor out the factorial and the power function here is, so it's always 3 members in the denominator and 3 in the numerator. But also, as we want to estimate something, all numbers that we multiply in the denominator are less or equal than the number that is strictly above it in the numerator. So
also for the first one there. So
yeah, it's the same happening here in the first one and also in the second one. But yeah, if another observation that we can make is we can cancel out this number here. So what we would see is that we have a 1 times, and then let's look also at the pink part here. It would be 2 over 3 to the 2. So in some sense, we already see some type of trend here. So the sequence members get smaller and smaller each time. And we have, like a power law that is already characterizing this trend. Yeah, we have here we have a power of 2. Here we have a power of 3. And so, I would say, yeah.
Maybe you can remark there that we need for the convergence that it converges to 0. So the sequence inside the series need to converge to 0. Otherwise, it can't be convergent as a series. So this is the first check we have now. That's not sufficient. It's necessary. So, but it gives us the idea that this should be or could be convergent. But we don't know yet what it means. But you will tell us, I guess.
Yes, so we will get to the bottom of it. This I can promise you. So, as a last example, before we try making a rigorous statement here, let's also factor out quickly the fourth element. So here we have 4 times 3 times 2 times 1, and 4 times 4 times 4 times 4. And if I mark the same section again, so the last 2 factors in the numerator and the last 2 factors in the denominator, I see that the behavior here is once again the same.
Yeah, looks very similar.
We have a 2 over 4 to the 2. And now let's look at the part that is in front. So I mark this with a light blue. So we have once again a 1-to-1 correspondence between each of the factors. The number is the same. And we see, or we observe, that each of the factors in the denominator is less or equal than the factor that is above it in the numerator. So what we can do is now we can just estimate it. So this blue section, we can just estimate this by 1. Yeah, so this is less or equal than 1. Yes. So. All right. So that's about the examples that we have here, and the tendency or a trend that we can observe and that we want to prove next is, well, if I look at the nth element of the sequence, can we then show that it is less or equal than 1 times 2 to the n squared? So this will be the idea here. And also to give you an outlook, so we have now already seen, okay, it may be possible to prove convergence, and we want to do it now with a comparison test. And so what we need to identify is a so-called majorand, or a sequence of elements that is always greater or equal than our original sequence of elements. And for the new sequence of elements, we already know that it converges. So you may recall that the sequence, that the series of 1 over n squared summed that this is a convergent series. So we want to estimate the sequence an against, well, a scalar multiple of 1 over n squared.
Yeah, so you need
Does
to
this
know...
sound like a fair approach?
Yeah, it's fair. You need to know that 1 over n squared as a series is convergent, and then you can choose it as a majorand for this one. This is the idea here. You could also choose another one if you know another one that is convergent, but this seems like the natural choice, like the simplest one that does the job.
Yes. So let's show that this inequality here holds, and it works in the same way as before. So let's just write it out quickly. So we have n squared over n. We have the factorial of n over n to the n. So, and if we expand this factorial of n, we have n times n minus 1, and so on, until we hit, well, this last part, 3 times 2 times 1. So each of our factorials will look like this. So let me make a straight line here.
Yes, nice.
So, and the same happens in the denominator. So here we have n times, and so on. And also we end here with 3 n's. Perfect. Now we can once again mark this pink section here. Yeah, we have it for all n now.
Maybe to emphasize again, you have n factors in the numerator and n factors in the denominator. So they fit together.
Yes. And then we have the rest here. So this will be then n minus 2 factors that we can once again, as above, estimate by 1. So this will give me this 1 here. And we have these 2 factors, 2 times 1 over n times n, which gives me 2 over n squared. So this inequality is actually true. And so this holds for all n that are greater or equal than 5.
5?
Yeah, so we have shown something for A1, A2, A3, A4. So we have some estimate here. We have something that works well. I would say maybe we can correct it and say it holds for every n greater or equal than 3. Because so I do not want to make it too confusing if n is 2 or is 1, because then this blue part won't make much sense.
For the middle part, you mean?
Yeah, for the middle part. So the estimate in the end will hold for all n. So let's...
But you're you're right. It's not important what happens for the first members at all. Yeah, you just need this behavior at some point. Yeah, so n greater than 5 is totally sufficient. You can just ignore the first members if you want.
We can ignore the first members, but we can. So the idea now for the for this comparison test is that we introduce a new sequence that we want to sum up. And make it a convergent series. And what I now define is a sequence that I call Bn. And so Bn is now defined for every n greater or equal than 5. And I can also use this inequality here to define the term B4. I will also use this part to define B3. I will also use this guy here and define it as B2. And I will estimate this here by 2 over
1 squared?
1 squared. No, 2 over 1. And say, well, this will be my B1.
Nice.
So now I have a new sequence that is called Bn, and what we can now observe is that, well, actually the absolute value, which is the same as An, because the sequence members are all positive, is less or equal than Bn for all natural numbers.
For all indices.
Yeah,
That's very
for
nice.
all indices. And a further observation, or this is something that we should recall from earlier sessions in real analysis, is that the series over all Bn's, when n goes from 1 to infinity, converges. So it also converges absolutely.
That's what we need for a major end,
Yeah.
for the comparison test. Yeah, so that's important.
Yes.
Choose a correct sequence Bn.
Yes. And you named it already. So the comparison test now tells us that given these two ingredients, also our sequence over the ANs converges absolutely. So by the comparison test.
Can you remind us of the definition of absolute convergence?
Yes. So absolute convergence is defined for series. So a series like AN can converge absolutely if the series of absolute values converges. So let me write this here. So absolute convergence.
Yeah, indeed.
So the series AN converges absolutely. By definition. So this term here is going to be defined. If another series, namely, so it looks very similar, but I have this absolute value here around each sequence member.
Yeah. So if you ignore the signs, so if you have negative, positive signs in this series, you ignore it, you just add them up with absolute values. So you see it's a stronger requirement.
Yes, it's stronger. And so I think, Julian, there is a classical example that tells you that not every convergence sequence also converges absolutely.
Yes,
maybe we should also state this one.
Yeah, we know the Leibniz criterion. And exactly this Leibniz criterion tells us already that there are sequences or series that are convergent, but not absolutely convergent.
Yeah.
So absolutely convergent is indeed stronger. And something that does not make a difference here in this whole exercise, because everything is positive anyway. So the absolute value does not change anything. But it's good to recall the definition again, because the comparison test tells you about absolute convergence, because you need the absolute value for this estimate. Yeah, so that what Fabian wrote there with the absolute value is less or equal than Bn, this is needed for the comparison test. Yeah, because it could be very negative, and then you could have this inequality. So therefore, don't forget the absolute value if there are signs involved, which is not the case here. So not a problem here. A sequence of convergence needs not to be, I would say, a series. So your last sentence you wrote there, this should be about series.
Yeah.
And the series is the...
You're completely right. Yeah, thank you for pointing that out.
Yes, because we are talking about series here. So an infinite sum. Yeah, and there different signs can cancel out in the summation, and therefore we can have convergence indeed, but not absolute convergence in this sense, which we don't discuss here at all because everything was positive. And Fabian now showed that this series, and maybe we scroll up again to see the exercise. So this strange series with the factorial and the n to the power n in the denominator, this is, now we know it, it's convergent by comparison test.
All right.
So this tells us something we might already know, that n to the power n grows faster than n factorial. So because it needs to grow faster such that this series is convergent. If it would be the same rate, yeah, this series will not converge. So therefore, this is the same proof in the sense. Okay, do we have any questions here?
So I'm checking the chat, but
yeah, it's worth mentioning the positive and negative parts of a series. Yes, that's what we do in the Leibniz criterion. So I have a video about the Leibniz criterion in the real analysis series. So there we exactly discuss that positive and negative parts can cancel out and make the series convergent. But still, it can happen that the whole series is not absolutely convergent. So that's important to remember when we talk about absolute convergence in this case. Maybe also interesting, this whole comparison test also works for complex series. So if we have complex numbers involved, then absolutely convergence means we have a real series again. So we can talk about that, and then we know that also this complex series is convergent. So this helps.
That's a very good point, because the comparison always uses, well, a symbol for the comparison that needs some sort of order, and this order already gets lost once we are in the complex numbers or also in other vector spaces with a norm. So this absolute value, it gives us something, as you just said, that holds in a far more general setting.
Indeed. And complex series is something that happens indeed, because it's not so complicated. There's a real part and plus I imaginary part. So you have two series involved, but you don't have to care about two series if you know the comparison test. Then maybe you can immediately tell this is convergent by comparison test, and therefore it works. It's well defined. But maybe we don't talk about complex numbers here, because I wanted to do exercise about real analysis. So but just to keep in mind, we can just translate this into complex analysis as well. There's a question in the chat if it's possible to calculate this sum, so the series. So what is the value of the series? And what can we say there?
That's a fair question. So it would be nice if it would be possible. And so actually I don't know for this example. We can use a calculator or a program to approximate this value easily.
Can you scroll up a little bit more? Yeah.
But so I think we have also some examples prepared where we really calculate the limit.
I will do one example now. But the answer here is we can't calculate the series with these methods here. We can just say it's convergent, which is already strong. We know it's well defined, so we can calculate with this number because it's a well defined number, and we can approximate it as well. But I don't know the solution there, so I don't know which value this sum has, and I'm not so sure how you would calculate that.
No, so I'm also not sure. And to answer one question that also came up in the chat, we will come back if time allows. I would say also to the second example here.
Well, what does it mean if time allows?
So we have the time.
We have infinite time. Yeah, so we just do all the exercises, and we hope it's not too long in the end. We just shift to my exercise because it fits in now, because there was a question about can we calculate it. I have an exercise prepared where we can do it. So let's go to my exercise here. So very good. I hope you can see it. Fabian can tell me if there's something wrong. Otherwise, I can start with the exercise you see here. This one is also a series, in real analysis. So we have real numbers here. It's not so complicated. Maybe by something what Fabian did now, you can also see it should be convergent because it looks like 1 over n squared. And we can do that, but I want to do another approach, an approach which actually calculates the series in the end. And there we will practice the partial fraction decomposition. So with this series, we can do partial fraction decomposition and actually calculate the value. And this is written in the exercise. We will show the limit is 1. So Python says the series converges to about 1.88. Yeah, as I said, you can approximate, and I think that's an approximation. And yeah, but let's talk about this later again. Maybe we start with this one first. So I will copy my series here, and then we go with A. Show by using partial fraction decomposition that the series is convergent with limit 1. So I copy that here. Maybe you ignore all the exercises. So this one is the series, and now we do partial fraction decomposition. What does it mean? This one is the fraction where we now use partial fraction decomposition. Not a strange concept. Okay, maybe that's good enough. Not a strange concept, and always helpful if you integrate or if you calculate series here, because it makes a complicated fraction into simpler parts. Yeah, it transforms it into simpler parts you can actually calculate with. And here, this would be, yeah, maybe I write it with coefficients first. This would be 1 over n and 1 over n plus 1. These are the partial fractions because, yeah, it's already factorized on the left-hand side. Yeah, so we have the one fraction, 1 over n, and n plus 1. So now you can always make this approach here. Yeah, so some could call that an ansatz. Yeah, so you start with something and then you show it's possible. So what we do is we calculate these coefficients. So how do we do that? Yeah, maybe Fabian, you know how to do that. There's one simple approach, one simple first step.
So I think the best approach would be to compare the coefficients that we have on the left-hand side and on the right-hand side, because you already wrote an equal sign there.
Indeed. But it's hard to compare now coefficients.
No.
Yeah, we need to make polynomials out of that. That's the idea.
Yes.
So, and to make polynomials out means get rid of the fractions. So multiply by the whole denominator. So
yeah,
on both sides. So I would say here multiply by n plus 1. And then Fabian is completely correct. The coefficients should be the same on the left and the right hand side because they are both polynomials. So the coefficients should be the same if the polynomials are the same. This is the idea. So, but I write down the whole calculation because it's used so many times. So it's good to see how one uses that. So I already canceled the denominator here and here. Yeah, this is what remains if we multiply with that. So, but to see the coefficients, you have to rearrange it. So always do that. Just write coefficients in front of n and 1 and n squared and so on. So here we don't have n squared. The highest power that is involved is 1, n to the power 1. So n to the power 1 times. So now the coefficient would be here a and b, a plus b. Coefficient for n. And the coefficient for the constant is just a. So I can also write a 1 times a, if you want that. Yeah, so these are the parts in the polynomial, and the other parts are the coefficients. So here, the same on the left-hand side. So this means you always get a system of linear equations. Yeah, because you have only linear factors for a and b here. So, and that's what we solve now. So maybe I write it down. A system of linear equations. Here it's very easy, so you don't need to do it, but I want to show you, you always have to solve a system of linear equations, so you can do it if you know some linear algebra. So in this case here, I write it as a matrix vector multiplication. So this is coefficient A, coefficient B, and the right-hand side. So first coefficient says A plus B is 0, because there's no n involved on the left-hand side. So we have here a 1, 1, a plus b is 0. And the second equation reads the coefficient in front of 1, a is 1. So we have 1, 0 is equal to 1. Okay.
Maybe it also helps to think about the left-hand side of the equality that you have there with the 1, to also think of it as a polynomial in the variable n. So you see where the coefficient maybe comes from.
This is an n to the power 0, you mean?
Yeah,
the
we have an
here.
n to the power of 0, and we also have an n to the power of 1, but with a prefactor of 0 on the left-hand side.
Yes, we can, maybe it's helpful to rewrite the left-hand side here as 0 times n to the power 1 plus 1 to the power 1 times n to the power 0. If you want that, yeah, because that helps indeed. Yeah, so we add the 0 here, and then we compare the coefficients. Yeah, so this 0 is indeed this one, and this one needs to be this a. And so I hope this is clear with this calculation. This always happens, also for very complicated partial fraction decompositions. You get a system of linear equations you can solve. So should we solve that, or is it clear? So maybe it's already clear. You see in the second equation, you see that a needs to be 1, and combine that with the first equation, you see that b has to be -1. Yeah, that's the solution. There's only one solution, one unique solution of the whole system. So, which is very good, because it means this one we had as an approach, as an ansatz at the start, we can now change to the real thing. Yeah, we know now that a is equal to 1, and we know that b is equal to -1. So this is correct. We can rewrite this fraction as these partial fractions. Which also means now we can, now the sum is not there anymore, but I will copy it here. Which means now we can rewrite this whole series with 2 partial fractions. So, but the problem is, it's clear with some sketch paper. Yes, you can have some paper in front of you and also calculate. Otherwise, you just ask questions in the chat. Then we try to help. So now I want to put in the partial fractions into the series, but we need to be careful. We can't just split it up into 2. And we immediately see why this is not possible, because we have 1 over n then. So if the series is 1 over n, it's divergent. Yeah, that's the harmonic series, the best example of a divergent series. And yeah, then you have addition or subtraction of infinities. Not good for calculations. Yeah, so that does not help. Yeah, so it's indeed not meaningful. So we will not do that. Yes, I don't know what the convergence on manifolds means in the question, but we do some real analysis exercises here. So let's talk about more complicated stuff at another point. So what you can do here is you just change to the partial sums. A series is the sequence of the partial sums. So let's put an index n here, and maybe give it a name. Let's call it capital Sn, as I always do it. So this is the partial sum. So this is well defined for each index n. And there we can do our substitution with the 2 sums. Yeah, so we write the one partial fraction and the other one, so we put that together. This is now my idea, I just copied that. So, and then we have minus the other one, yeah, because I just can put the minus in front, and then we have 1 over n plus 1. And both go from n is equal to 1, yeah, so the lowercase n to capital N. So at this point, this is well defined, and now we can do something we call telescoping. This works for some special sums, and if you see something like that, that the 2 partial fractions look almost similar, this is an approach you can just try out. Yeah, if it works, then you get the result. So now what does it mean? We can see that if we write the parts, or all the sequence members here, that we have the same there, and with different signs. So they cancel out. So what you do is then shift the second sum. Maybe we need a new coefficient here. I would say we can choose k. So k could be n plus 1. So if k is n plus 1, then this is just 1 over k. which is the same as the first series. So that's what we want. Yeah, we exchange some indices to see that they look the same. So maybe I just copy that. And then we do the substitution here. So now k instead of n means now we start at 2, because lowercase n started at 1 and now we start at 2. But now we also go to capital N plus 1. Yeah, so we go further than before because we shifted by 1. So, but otherwise it is exactly the same, but just with 1 over k now. So not so complicated, but now it looks the same as the first one. But the indices are not the same. And so we can't just say this is 0 because it looks the same, because we also have to consider all the indices involved here. And therefore we have to change a little bit. I would say we also ignore the first sequence member here by putting it in front. So now we write 1, which is putting in n is equal to 1 into the series or into the sequence 1 over n, which means now we can start with 2 here as well. Now, Fabian, you check if I do some strange mistakes. Then please.
So far, it looks very good.
Okay, I'm relieved with that. Okay, so with a lot of indices, you can make mistakes. But here it's important that you use the correct numbers, because it's important that you check that you have all sequence members involved. So the same here. I just want to go to capital N, because the first one does that. So I have to put the last one out. The last one here is putting capital N plus 1 into the sequence 1 over k. So we have 1 over n plus 1 here. With the minus sign. Yeah, so maybe not so important, but you have the minus sign. So now the middle part. The middle part is what we call this telescoping sum. Because it puts, you can put it together like a telescope. It's like the picture. You have this telescope you can make long and small. I don't know if you use that in these times, because you just have a smartphone, I don't know. But if a telescope, you could just make it small. And this is what happens here. You put it together and it just vanishes. Or to be more precise, the first and the last part remains of this telescope. And this is the first part is the 1, and the last part is the minus 1 over n plus 1. And the middle part vanishes, because now it's actually the same. Yeah, it's exactly the same sum, finite sum, to be more precise. Yeah, so this one we can note is equal to 0. So what remains now is that we know that the partial sum, the sequence of the partial sums, is 1 minus 1 over n plus 1. Yeah, so the whole series can be now rewritten as this equation. And there we see it's convergent, because now we can do the limit capital N to infinity, which is not hard because we know this is a sequence that converges to 0. So if that goes to infinity, this part goes to 0, so only 1 remains, which means the series is convergent and has limit 1. Yeah, so maybe I'll scroll up again. We started with this series here, which was very nice. And this series is now 1 as a value. Yeah, we calculated the value of this series. Yeah, so we get Fabian?
Yeah, the interesting part about this telescoping argument is that you see that even though we wrote the original question as a problem of a series, we see that it's all about just calculating the limit of a sequence. So in some sense the sequence that we have, the sequence Sn, was just disguised in form as of a series, which makes it then very easy to calculate the limit in the end.
Yeah. Okay, but disguised as a sequence, in a simple sequence in this sense. Because we know that all series are sequences by definition, because we define it as the sequence of partial sums. But now it turns out that this partial sum, this capital S, capital N, I called it like that, that this one is a very simple sequence. This is what we found out, yeah, by the telescoping. That's the fun part indeed. The telescoping tells us that the series was not complicated at all. It just looks complicated in this term. But actually, a lot of parts just vanish in the middle. Yeah, so if you write that, and that's what Fabian did at the beginning, you just check the first coefficients, then you would also see that. Then you could also say, maybe I proved that by induction or something. Yeah, but telescoping is something which works naturally in this case. Just write it down and then you see that this cancels indeed in general. And then you know now all the values of the series or all the sequence members Sn. Yeah, but we are interested in the limit. So therefore that the limit is 1 is very nice here. Okay. I don't see any questions about this exercise. So maybe we go to part B of my exercise here. So part B was a new sequence or a new series indeed. Maybe I copy that here again. So now a new series comes in. I called it S, but just because we want to calculate the limit as well. But now we want to show that this series is convergent. Yeah, we can do the comparison test as before, but I wrote the exercise like, okay, use what we already know from part A, so that this one is convergent. So which means, yeah, don't use the comparison test with 1 over n squared, use this one and check if it works. Yeah, because that's how I designed this exercise, that it works. And then you see, you can compare it with other series or other sequences as well. And yeah, just let's do it, because this is not too complicated. So comparison test means this one, if it's convergent, should be dominated by one we already know is convergent. And indeed, what could be helpful is that it is dominated by n plus 1. So if we have that, yeah, the major criterion, this comparison test from before tells us that the new series is also convergent. Therefore, we have to do that. Hi in the chat. It's always nice when you say hi, then we know that you are there. And you can just ask questions or any comments you want there. So we want to show that. Therefore, I go backwards now. I want to check if I can show that with some assumption which is easily seen. And therefore, first step I want to do is use the reciprocal here, which means I exchanged the direction of the inequality. Please note everything is positive, so we can just multiply this, and that works. So we have n plus 1 here. So this is equivalent, no problem there. Let's see if we can make it even easier. So there we have n squared plus n. So I can subtract 1n squared. So I have 3n squared minus 1 is greater than n. So maybe also put the 1 on the other side. Works. 3n squared, and then we have n plus 1. Okay, there I already see this works. This is indeed correct, but I can also make it simpler by dividing our n squared, because then we have 1 over n plus 1 over n squared here, which is obviously less than 2, or less or equal than 2. So indeed 3 is greater than that for all n, because this one is nicely dominated by that. Okay, so this one holds, this one is correct, and then we go backwards to the top again, and we know, this one also holds. And that means the comparison test tells us that the new series here, you can't see it anymore, and then now you can see it again, that the new series we defined here is also convergent. Yeah, indeed, we have found a nice majorant. Okay, is there a question here? Yeah, you're welcome. We are glad that solving problems helps. And that's my part B here. Part C would be to calculate the limit of this series, but I think we can do that afterwards. or after the second part of Fabian's exercise, just to make some change again in the explanation here. Otherwise, if you have questions about this, you can also ask about that later again. Okay, Fabian, I switch to your screen, or do you have any questions about or comments about my calculation here?
So no comments other than there are also different ways to do this estimation. So I think it's always a good idea to try to work out some of the calculations also on your own, or try to find also other ways to derive this this estimates, because there is not one correct solution. I would say there are different ways to prove it.
Indeed.
And yeah, but then let's come to a next example of a series that I brought with me. Yeah, it's from the structure. I think it's similar to the ones that that you presented earlier, because we have now two polynomials in the numerator and in the denominator, polynomials in n. Another thing to observe here is that the series does not start at 1.
Maybe you can scroll up again to see the whole exercise.
Yeah.
So, no, that's too much.
Yeah, that's better.
Yeah, that's good. And yeah, we want to show divergence or convergence of the series again.
Yes. So, yeah, so the first, we will do it once again in 2 steps, I would say. The first would be to get an intuition, because this is a more or less open question. It does not tell us, does it converge or not? So the first step will be to first get a feel again for how the series behaves, to take a decision on whether we want to prove convergence or divergence. And for this, again, it will help to get a feel for, well, the trend that our the sequence members here that we are summing up, how they behave. So yeah, and what I wanted to point out is that this series starts at n equals 2. Yeah, sometimes this is just confusion. Sometimes it's necessary, and in this case, it should indeed be necessary, because if we plug in n equals 1, we would get a problem here in the denominator. So, but it it is not important where the series starts.
So we would get 0 in the denominator, so
yeah,
that would not be defined. So if you see that, then it's just a typo. So sometimes people forget that they have to shift that for the first case, because as always, we are interested in the behavior n to infinity. So you can start wherever you want, and usually you start when it makes sense, where it makes sense.
Yeah. So then let's start with the first part in our proof to find out whether we want to prove convergence or divergence. So I'll copy again the sequence that we are summing up. So it's n plus 5 over n squared minus 2n plus 1. And something that is done a lot when one looks at limits of sequences that consists of fractions of polynomials is that one factors out the highest power to get a feel about the asymptotic behavior of this fraction. And we see here, so the highest power in the numerator is n, and the highest power in the denominator is n squared. So so what I did here was I factored out 2 times just the n, and then I have 1 plus 5 over n, and in the remaining part I have n minus 2 plus 1 over n. So these cancel out, and now I have a fraction that will help me to see what happens when n goes to infinity. So in the upper part, I see that I have 1 plus 5 over n if n goes to infinity So the denominator goes to 1. On the lower part, I see that n goes to infinity and the rest here goes to -2 plus 0. So I would get a fraction that looks something like this, 1 over infinity. Let me delete this, because now you see what I'm getting at. This fraction is converging to 0, because, well, I have something here that grows to infinity and something here that stays bounded. So I have something that goes to 0, which is already good, because this is the necessary criterion we have for series convergence, that the sequence that we sum up is a null sequence. It converges to 0. However, this is not a sufficient criterion, but an analysis like this helps us to see the behavior of this sequence here. And what I want to point out is now, if we look at this part here, that was also crucial for determining whether it converges to 0 or not, we see that it some sort behaves like 1 over n. And now, coming back to the original question, we are summing up elements of a sequence that asymptotically behaves like 1 over n. What would your guess be? Is it a convergent or a divergent series?
My guess. Is it a question for me or for the public?
Whoever answers first.
Yes, because you already wrote it with 1 over n. So the behavior is like the harmonic series.
Yeah.
It's not so convergent usually. So if you use comparison tests, maybe try out the minor end criterion with the harmonic series. If it works, you have proven divergence. That would be my guess here.
Yeah, and that's exactly that. That's exactly the next step of our strategy now. So we have now set our goal. We want to prove that the sequence diverges. We want to do it again with a comparison test. And so our goal will be to show that an is greater or equal than, well, let's say some constant c times 1 over n. So I don't know whether this example, so usually you don't know whether this example will be that nice that you can just choose the constant c equals to 1. So I would just carry on with this constant and later fix it, because so the right hand side, no matter what I use for the c, except for 0, will be a divergent series. So let me copy the part that we also need here again, because I want to do some previous estimates. So what we saw here, copying the part where I already did some calculations, was that an equals.
There's some comment in the chat that someone did the ratio test and got the result it's divergent. So Fabian, can this work? Can you apply the ratio test and get the result?
So why shouldn't it work? So I think this is also a fair criterion to use.
Yes.
Here,
I think so too. Yeah.
There are many ways to do it, and yeah, it's really nice to see that you also did some tests on your own. Yeah, it just shows you that there is not one way to solve these problems.
No one wanted to interrupt you with your comparison test.
No.
Just as a reminder, of course, ratio test with this quotient you have, it's a good approach.
Yeah, very nice. Thanks for the comment. So we have now this form of our an, and the first estimate we can do, we have already set our goal. We want to come out at something c times 1 over n. So the first thing I want to get rid of is this 5 over n here. And this is always a positive number for all n in n, for all n in the natural numbers. So I can just do this first easy estimate, just get rid of the green part, and then stay here at n minus 2 plus 1 over n. Okay. All right. So now I would do a little side calculation to find out whether this inequality holds true and for which value of C. For this, I take a closer look at the numerator here, at the denominator. So I will do it a little bit differently than we saw it before. I will start from something that I know is true, and then work up the calculations up to the point where I have this inequality that I want to show. So what I know is that minus 2 plus 1 over n is less or equal than 0. Yeah, this is an obvious statement here because n is always a number that is greater or equal than 2, because these are the indices that we are using to sum up. So what I now do is I add plus n on both sides of this inequality, and I get n minus 2 plus 1 over n is less or equal than n. So this still holds for all n greater or equal than 2. So now I can reformulate this because I already know that n is greater or equal than 2 to see that's okay, it's 2 minus 2 plus 1 over n. Yeah, I'm just estimating now to the left this n by the fact that n is greater or equal than 2. And I do this to conclude that, well, everything that I have just here on the right-hand side is greater or equal than 0. This will allow me to now use a nice division here. Namely, now I divide on both sides by n, and I also divide by n minus 2 plus 1 over n, from which I know it's a positive number. And this gives me 1 over n less or equal than 1 over n minus 2 plus 1 over n.
Mm-hmm.
And this still holds for all n greater or equal than 2. So now, coming back to what we originally wanted to prove, we wanted to see whether this inequality here holds for a certain value of C. Now let's look at what we have shown. We have a 1 here, and we have also an inequality that looks just like the one that we want to prove, with C equals to 1, and it holds for all n greater than 2.
Nice.
So far, so good. We have now shown that an is greater or equal than 1 over n for all n greater or equal than 2. We can now do the comparison test, because we have now found, well, a comparison of our original series with a series from which we know that it diverges. So to make it more formal, we now define the sequence Bn as 1 over n for n greater or equal than 2. And we have shown here, I can delete now this question mark because it holds true. We have shown this inequality here, that is called with star, that an is greater or equal than bn for all n greater or equal than 2.
Yeah, so this is the comparison test with the minor end criterion. So we show it's greater than a series or a sequence. Each sequence member is greater or equal. And we already know that this sequence given in the series is divergent. So
yes, so I just added this as well. So we have both ingredients that we need for the comparison test. A nice estimate, and it's an estimate versus a series that diverges. So summing up or concluding this proof, we know that the series over all ANs diverges by the comparison test. Oh, sorry.
Yes, and I would always do that in this case. If you see the harmonic series, do the comparison test. Do some estimate there, And you just have to show it in the limit. So Fabian was very strict here, showing the inequality for all n in the series. That's not needed. You just need it at some point. Yeah. So if you can show it for n greater than one constant, and you don't even have to know the constant. Yeah? You just have to show it works at some point. Yeah, that's enough.
Yeah.
That's the comparison test is very strong there. Just check if it works eventually, and then you're finished. And then, yeah, this makes this comparable to a lot of exercises. If you see the harmonic series, yeah, do some estimate and then prove it works at some point, and you're finished. So
yeah,
it's a typical,
so you see
a typical exercise for an exam. That's what I can tell you. So therefore, it's a good.
The main part I would say is just spotting
that
the harmonic series somewhere, and then just going for the estimate, however you want to use it.
Yeah, but we can go back to the question if you can use the ratio test, because there was the comment in the chat. Yeah, the ratio test gives us 1, so not something that is helpful.
Oh, and okay, so that's interesting then. So it could then just happen that you start out with this question, you do the ratio test, and then you see, oh, no, I cannot work it out.
Yes.
Then, well, there is another criterion at your hand that you can use.
Indeed. I think it's always good to just use ratio test or the root test if it looks good. If it does not give you no result, then do something else. Yeah, but doing the test is very quick, so you can always try. Your last exam is on this stuff. Yes. Then you should know it.
Perfect. That's what we were hoping for, that it will be helpful for you in your exams, of course.
Yes. So we were hoping, we solved some exercises here. So this is very explicit. Yeah, you see that Fabian did these estimates, something you usually would not do in a video explaining the topic, because it's just too messy. Yeah. So therefore, we do this now live that you see. Yeah, sometimes it's messy to calculate. That's just how it is. But you have to get the whole picture. You need to know where to go. You need to know what to show. And then you try filling in the gaps. Yeah, and that's what we did here. And then you know, you can apply the comparison test. You know how it works. Yeah, this live stream will be saved. No problem there.
Yeah, great. So it's also a nice comment here. So we save it, and then you can rewatch it, or then download the exercises that are also linked in the description, and do it, I say, in 1 or 2 weeks on your own again, and then rewatch the video if you don't can work it out on yourself. Because
this is the first live stream we do together here. I hope it works. I hope that YouTube saves the live stream, because I didn't do a recording locally. So maybe next time I do that.
I will see how it works out, but yeah.
Yes.
We'll see.
No, it should be saved. I guess it would be saved. I'm not so sure what YouTube does. Usually the other live streams were also saved, so I guess it's okay. Okay. Other questions for this exercise here? I'm very happy. This was a nice calculation. And yeah, these problems all look similar. If you recognize the harmonic series, do some calculation to get an estimate there. And then you get the comparison test, and you're finished. But the first part is that you find it. Collaboration, I don't know. But we can do a lot of live streams here, if this works. Let's see. Then I can do my exercise.
Yeah, there was still something missing on your part of the exercise sheet.
Indeed.
Let's do it.
Let's change the screen again. Okay. Now it's up again. So maybe there's some second missing. But Fabian, you can still hear me.
I can hear you.
Okay, perfect. Okay.
But yes, there was also some buffering on YouTube that I also saw.
Yeah, that was indeed the case. So some frames are missing now, but I guess that's not a problem. Okay, this is my part C. So we calculate the limit of the series. We already know it's convergent. So we know it has a value. The series has a value. And usually we can't calculate it because it's too complicated. We saw that with the first example of Fabian. This was, we could show it's convergent, but we didn't know how to calculate the value. So here, this looks similar, but there it's possible to calculate the value by using the partial fraction decomposition and the telescoping trick again. So sometimes it happens that you can do it. And now we do it with that. So we know it's convergent, so that's not a problem. But also this trick with the telescoping sum shows the convergence. So we could skip part B if you want, but I included that you can see the comparison test again. Okay, now partial fraction decomposition means we have to write that as a factor of two fractions again. So maybe I do that here. So this one is 1 divided by, so now what are the factors here? I could write it as 2n plus 1 and 2n minus 1.
So you spotted the binomial formula there.
Yes, but, if you want to call it that way, maybe I write it in the other direction. First the minus, then the plus.
But you could also look for zeros if you look at it as a polynomial, or how do you come up with these linear factors?
Yes, of course, you look for the zeros and then you split it up. So, and then you can also rewrite it. You could put the factor 2 we can pull out if you want. Yeah, so it doesn't matter so much. The important part is that you have linear factors. Yeah, so n with power 1. So yeah, binomial formula, if you want to call it that, is just factorize. So with the minus sign there. Yeah, you have to spot it. Yeah, indeed. But there's no magic. Not that this is the point here. You just have, you see, you can split it up into that. Okay. And then partial fraction decomposition as before. Now maybe I don't write it here. Let's write it here. Means we have one fraction with the minus sign plus the other fraction with the plus sign. Okay. So again, two coefficients I call capital A and capital B as before. And now we have to find them. So I asked that before, Fabian. We have to multiply with the whole denominator to get rid of the fractions and just have polynomials. Because for polynomials, we can do this coefficient comparison. So we can compare the coefficients and have, again, a system we can solve. So, okay, should I write it down? Yeah, we multiply with that part and the other part, which means here we cancel the one part and there we cancel the other part. So this is equivalent to 1 is equal to A 2n plus 1 plus B 2n minus 1. So now, again, as before, we have a polynomial on the left-hand side and we have to write the coefficients on the right-hand side, which means I would write n. Yeah, we don't have n squared here as all, at all, so we just have n. And now I just try to do it. Fabian, you are with me if I do it correctly?
Yeah.
So we have 2a and 2b, and the coefficient for 1 would be a minus b.
That sounds about right.
Yeah, very good. So you can also do some intermediate steps to make sure that you transform it correctly. So, but now this is what we compare again. This is on the left-hand side is a 0. It's not there. Yeah, the coefficient in front of n. The other one is there. It's the coefficient in front of 1. Yeah, so it's just 1 here. Yeah, so again, a simple system of linear equations. Let's write it down as a system. Again, let's write it in the general form as a matrix vector multiplication. C is convergent. Yeah. If that's the question. Yeah. So now, A plus B. So first we have 2 and 2, which goes to 0. and then we have 1 and -1, which goes to 0. So I write it in this way, just because we can always practice linear algebra.
So I think in the last 0 should actually be a 1.
Oh, thank
right?
you.
Because it's a minus b should equal the factor 1 that you underlined there.
Yeah, good that you said. This is the blue, and this one was the red on the left hand side here. Indeed, so that was my quick mistake by writing it down. Because I'm so intrigued by linear algebra here, so you need to know a linear algebra because you use it so often. So therefore I write it as a system you want to solve and do the row operations to solve it. Maybe you don't need to do that because it's just a 2 times 2 system, but it's always good to write it in general form and do it how you would do it for a big system as well, such that you don't forget how to do it. So what can we do? We can multiply the first row with 1/2 to make it simpler immediately. And this one is the 1. And then we can just, maybe I'll write it down. We can just subtract the first row here in the second row. Which means now we have, the first row is still the same. Yeah, so no problem there. But the other one now is 0 here. And we subtract it, so I think we have -2 there and still 1 here. So now this is in the triangular form, so the system is solved, essentially. Yeah, now it's just backwards substitution for the variables. Yeah, so you always want to get this triangular form. Okay, not so complicated. We immediately can see the solution. We have b, the second component, the second coefficient here, as -1/2. Yeah, for this equation. And then we immediately get that the first one has to be 1/2 plus 1/2. Okay. Yeah, you see the chat, Fabian. I don't see any questions about this here.
So there's some of our viewers already calculated the limit in advance, and I think we're already about to do it now.
Yes, yes. It's good. It's good that you calculated that. Okay, so now we have the coefficients, so we can copy that from above again. Our approach at the beginning was that, and now we have A and B. So now I can fill in the details. We know this one was A, so this is +1/2, this is -1/2. So very nice. And now we do the partial sum again and do the telescoping. Yeah, so this is the same as before. I write down a sum here that starts, I think it started at 1 as well. And now it goes to capital N. And now we have it here as well. So, and now you might already see, I just put it in front. I hope that's still readable here. Okay, now we have the telescoping, if you see it again, because this one is shifted. So maybe let's pull the 1/2 factor out, then it's easier to read. Yeah, so I copy that again. And then we have 1 divided by 2n minus 1. Yeah, minus. Yeah, so now the same thing, just with a plus sign there. Oops, the sigma is missing. Just with a plus sign there, which means we can do our index shift here again. So this is the same index shift as before. Yeah, we put in k as n plus 1. Yeah, why does it help? Because we can rewrite this as 2n plus 1 minus 1. I hope you can see that. This is the same in the denominator there. So if we put in k, it has the same form as the first sum. Yeah, exactly the same form. So maybe let's copy that again and let's do this live. Yeah, we put in k, 1, 2k minus 1, but now we have to start with 2 and go to n, capital N plus 1. It takes 10 seconds.
Yeah, so apparently there's a faster way to calculate it, but I would say let's first finish your approach on the telescoping sum.
Yes, we want to do the telescoping sum because that
Yeah.
was the exercise. It does not matter if there's a faster way. This was the exercise. We solve the exercise as is given. Okay, then 1/2, and now we pull out the first factor again, which is 1, and now we have to be careful. What is it? It's 1 divided by 1. I hope this is correct. Yeah. So now n starts at 2 here. We go to capital N again, and then the same as before. So maybe I can do it quickly because we already discussed how this works. And now we also have this from k, from 2 to capital N, 2k minus 1, and the last factor we have to get out again, which is here n plus 1. We put in n plus 1, so we can write it as 2n plus 1 minus 1. No, it's not readable here. Maybe I write it as plus again. So if we calculate it, it's 1 divided by 2n plus 1. Okay, so again, we see we have here the middle part, the telescoping sum, which is equal to 0. So this cancels out, and first part and the last member of the sequence remains exactly as before. So telescoping works here, and then the result is 1/2, which was already spoiled in the chat, but not so hard to see. Yes, you can just write it as 1/2, and then this remaining factor. Yeah, so indeed, as before, we have the whole series. For every partial sum, we have a value, which is very nice if you are interested in that. But it's also nice in the limit, because now the limit is 1/2. So of course, if there's another way to calculate that, you can put it into the chat. That's no problem. But the point of this exercise was that we calculate with the telescoping sum. So we practice partial fraction decomposition. That's what I did with our nice system of linear equations before. We put it together into the partial fractions, and we do telescoping. Because telescoping is always nice if it works. Yeah, you need the correct sequence, the correct series, and then you can do it. And then the limit is now 1/2. So
something also to add, I would say if you do practice this a lot, then you will see that certain elements repeat over and over again, that you do not need to write down everything in detail as we just did here today. So this was already with a great level of detail that you can follow through the steps that we did. But sometimes you may just spot it right away. Oh, it's a telescoping sum, because you have done it over and over again, and then it's then you can save yourself some paper and just write down the limit quite easily. But you need to get there.
I would also say
get there by practice.
I would also say sometimes you don't have to solve the system of linear equations, because you can also spot how the partial fraction decomposition should look like, and then you can just guess the coefficients, and then you see, it works just by multiplying. This is indeed correct, or the one sign is incorrect, and I changed that. Yeah, of course you can make it very fast if you are used to that. Yeah, and then as Fabian said, you spot telescoping sum, so I immediately write down the first and the last entry and don't care about this index shift, because I know how to do it and it will work out. Okay. I don't get it completely what is written in the chat, but maybe someone gets it, and then it's also good. We know that S1n squared converges. Yes. But we want to calculate the limit. So this does not get us the limit 1/2. So it's not quite the solution I was looking for. But also okay. Now we talked about this before. comparison test works here easily to show that the series is convergent.
Yes, so you do not need to get to the whole trouble of finding the limit if the question is just, does it converge or doesn't it?
Yeah, that's a good point. Yeah.
So this is also something, as some of you are preparing for an exam, really study the question before getting into it, because you see there's a great difference in the amount of work you need to put in once you want really to know the limit. You can't just spot that something converges on or doesn't, and then write down the criterion. But if you want really to calculate the limit, then it's asking you for an exact number, and then you need to put in some more work.
Yeah, indeed. I think it's a good point. You should read the question, maybe more than once, to see that you understood it, and then do the correct thing. So if the question is you want to calculate the limit with telescoping sum, yeah, then you need to do that. If the question is just about the convergence, yeah, that's what we did at the start of the video. So yeah, read the question. So okay, this is easy. Good. Problem solved. Okay, I don't see any questions in the chat, except for, yeah, you can do it in another way. So I would say we have calculated all the problems we presented. What do you think about the telescoping sum, Fabian?
Oh, it's always nice to see it come up. Yeah, it's a nice trick.
Yes, it's a nice trick.
You need to get used to it. Yeah, it's really confusing, I think, if you see it for the first time.
I think so too, but then it's really nice. But to be honest, if you see this sequence, or the whole series here, you don't see this telescoping sum immediately. Yeah, you just see it after the partial fraction decomposition. I don't see it in this written form.
No,
therefore,
no way.
Therefore, it's really helpful if it's mentioned in the exercise that you need to do the partial fraction decomposition, because then you see it. So then you see it works. Otherwise, yeah, you don't know how to do it. Yeah, but for the first one, the first exercise I showed you, there you should recognize this should be partial fraction, not partial fraction decomposition. This could be the telescoping sum because it's already shifted in this one. You don't see it. Sorry. In this one step, yeah, it's already shifted just by one index shift here. So there you could see the telescoping trick. Yeah, but you should always see it after this partial fraction decomposition. Yeah, so this was all I wanted to show you today. Do you have other exercise, Fabian, you want to show?
I have nothing prepared.
No, that's good. Just that I don't cut you short.
No, not at all. I think there are still plenty of exercises that we could cover. I would see we'll see how the feedback goes if we do it again, maybe on some different topic from real analysis. But yeah, I really liked the session today.
Yeah, that was indeed quite nice. So I think we can check which topics are interesting enough, and then we search some nice problems and solve them as well. And
yeah, when is the next live? Yeah. We should discuss this and then let you know, but hopefully soon.
Yeah, we'll do it soon, because now we have to set up. And
yes.
Yeah, and you can tell us if this is helpful, because if it's really helpful, yeah, we are motivated to do it again. And yeah, otherwise, just tell us what we can improve, then maybe we do that as well. So then, thanks for coming. You can always ask questions in the chat or in the comments under the video. No problem at all. Just put your questions there, we will see it. Okay, I thank you for coming. Thank you, Fabian, for calculating these nice comparison tests.
Thanks for having me.
I think that was very helpful for a lot of people, because this is such a standard exercise in a lot of exams. So it's good to see how you get through it. And yeah, Fabian, let's meet again. And everyone, have a nice day.
Have a nice day.